Hey everybody, let's do parallel circuits now, shall we? So I have here two circuits using the same components. And we want to talk about it and get a better understanding of how this is going to work out. All right, so here I have a circuit, 16-volt battery or power source, and the current comes down and it splits through two 4-ohm resistors. So the current now has a choice of which resistor it's going to go through. Not all the current goes through each resistor. As a matter of fact, because the resistances are equal, the current is going to split up equally. But what would have happened if I took those 4-ohm resistors and put them into this circuit? Okay, where I'm putting them in series with each other. Well, you can think of it as like two checkout lines. If you had to go through two checkout lines to get out of the store, does that help you or hurt you? I mean, if you had to go through one checkout line and then go through another, not that they are both open for you, but you have to go through a line and then go through another line. Twice as hard to get out. But what if two checkout counters were open for all the customers and you could pick either one to go through? Aren't you getting out a lot faster, even twice as fast? So in this series circuit, the two 4-ohm resistors would add up, this is the redraw for the series circuit, would add up to a total of 8 ohms. And in terms of that 16 volts, it would only allow 2 amps to go through. But if instead of lining them up one after another, in series if you will, if I put them parallel to each other, as here, well now what's going to happen? Are they making it easier or harder for the current to pass through this circuit? And I think you would agree that they are making it easier. So what does a redraw for this one look like? Well, 16 volts. Now let's be logical. By having two of these open, how much harder or easier is it for the current to get through? And I think you would realize in this case, it's twice as easy to get through, which has done what to the current? Made it substantially more, twice as much. So if it's twice as easy, what would the resistance on this be? I think you would recognize quickly this must be 2 ohms of resistance. It is very logical. All that 16 volts dropping over it, and if we are using I equals V over R, 16 volts over 2 ohms gives you 8 amps passing through that. Well, now let's put this back into here and you realize, hey, wait a second. Dirty little secret of parallel circuits. You don't really need to do a redraw, do you? Well, let's think about it. This 16 volts. 16 volts is between this point and this point. Okay? Between those 2 points. Well, look at this. This is on a wire, so there is no voltage drop between these 2 points. Meaning there's no voltage drop between these points and this. And at the same time, this here is connected in wires to this, so there's no voltage drop between these, thus no voltage drop between all of this. Meaning, if there's 16 volts between the red and the blue, there's also 16 volts between this red and blue. So the voltage drop across it, you already know, it's 16 volts in both cases. So if we're using I equals V over R, we can see right away that's going to be 4 amps going through that one and 4 amps going through that one. So why would we need a redraw in this case? I think perhaps you could see. How do you know if you're correct? We have a lot of details on these things and we can mess them up. But when I look down here and I see that this one has 8 amps going through the effective resistor, which is the 2 ohm resistor. That's what you get when you put these in parallel. When I see that you have 8 amps here and I have 4 amps and 4 amps, yes, that equals the 8 amps. So right away we know we have done this one correctly. So at very least, Without a redraw, you can't be sure you've done it correctly. But at most, when we move very quickly into hybrid circuits, a redraw is absolutely necessary to proceed. So get used to doing it. So let's do another one here. And this one's a little bit more complicated, but it brings out all the stuff we need to do. So we have then going to have a 19-volt battery, and we're going to use 3 resistances . 19 volts, and my first is 22 ohms. Then I have 11 ohms and 44 ohms of resistance. We will mark for each resistor. Well, now, the first thing we have to do is figure out what would the effective resistance be. So when I do a redraw here, what's a single resistor that would have the same resistance as all 3 of those combined? The formula is very clear here, and that is the formula using reciprocal. So 1 over 22 ohms plus 1 over 11 ohms plus 1 over 44 ohms. Now, what do I get when I do that? Well, when I do this, I get 0.159. Is that right? Is that right? Let's talk about the theory behind this and make sure we don't ever get this wrong. What's the lowest resistance this circuit could possibly have if I opened some of the resistors? Well, what if I opened this resistor and this resistor? So the only resistor where anything is coming down now is through the 11 ohm resistor. So the circuit would have a resistance of 11 ohms. That's the lowest resistor here. Well, by adding another way for electrons to get through, could I have made the overall circuit more resistive than 11 ohms? I mean, if you're trying to get people out of a store and there's just one checkout line open, and you open another one, even if that checkout person is new and not getting very many people through, isn't it still easier to get out of the store? I think you'd agree it is. So there's nothing, no resistor I can add that could make this circuit more resistive than that 11 ohms. So the lowest number, or rather the highest number I should have on my effective resistance, would be 11 ohms. The number has to be lower than that. But also consider this. What if this was 11 ohms? And what if this was also 11 ohms? What if they were all 11 ohms? Well, then it would be 1/3 as resistive as that 11 ohms, somewhere in like 3.5 or something like that. So it has to be greater than that amount of resistance. It has to be greater than 1/3 of 11, and it has to be less than 11. Is 0.159 anywhere in there? It's not. What did we forget to do? We forgot to take the reciprocal of this, because what all this equals is the reciprocal of the equivalent resistor. So when you get that number, hit the 1/x key one more time, and you will get 6.3 ohms. Now, does that satisfy our requirement? Is it less than 11? Yes. Is it more than 1/3 of 11? Yes. So 6.3 ohms is a far, far more reasonable number to have here. So this would be 6.3 ohms with a 19-volt drop across it, and that would give us approximately 3.0 amps. Of this, what comes up? Well, again, we already know the voltage drop across all of these, so really nothing comes up. What this does is allows us to check our work. So it's going to be a 19-volt drop here, a 19-volt drop here, and a 19-volt drop here. Then with our formula, I equals V over R, we could put it in. 19 volts divided by 22 ohms gives us 0.86 amps. 19 volts divided by 11 ohms gives us 1.79 amps. 19 volts divided by 44 ohms gives us 0.43 amps. So how do we know we did this correctly? Well, add these up. 0.86 amps plus 1.79 amps, or 1.7 amps, what I really have there, 1.7 amps, and 0.43 amps. You add these up and you get 2.99 amps. Pretty close to 3. So that's how you would check your work. Plus, much more importantly, that's what you need to be able to do to move then from parallel and series into the beautiful hybrid circuits. One other thing to talk about here. In series circuits, we talked about where an ammeter would go. That an ammeter could go maybe in the wire here like this. Could it go on either side? Could it go, yes, wherever you put it, it will measure the current flowing through that part of the wire. With the understanding that when you measure something, you do not want to change the thing you're measuring. So what does the resistance of the ammeter in this case have to be? It has to be approximately the resistance of the wire. That is, as low as possible. Great. If I want to measure the voltage, could I just put a voltmeter in here? Well, what's the voltage difference between this leg and this leg? It's in a wire. It should not have a voltage difference. So that would be useless to put the voltage meter there. The ammeter can certainly go there. The voltmeter, well, if I put another parallel across this resistor and put the voltmeter there, could I measure the voltage difference between this point, remember in blue, and this other point in red? Well, yeah, there's a resistor there, so there's going to be a voltage drop there. So I could put the voltmeter here, and I would measure the voltage drop across that. But once again, when we measure something, we do not want to change the thing we're measuring. So what should the resistance of that voltmeter be? Well, if I make a low resistance here, aren't I letting a huge amount of current flow across that? Yes. And if I did that, is that a lot like a short circuit? Yes, we make smoke if we do this. So if you did not have your meter set correctly and you measured it for amps across this, that would be bad. That would be a short circuit. You'd be doing bad things. We say making smoke. That's not good. So what should the resistance of a voltmeter be such that it can measure the voltage drop, which you get by just going across the resistor, but you don't want to change anything. You don't want the battery to know it's being measured. Well, obviously the voltmeter should have very, very high resistance. So a voltmeter, very high resistance, you tap across where a voltage drop would occur, which would be a resistor. Okay? Ammeter, you would never put an ammeter here because you'd short the circuit out. And a voltmeter here would not only turn off the circuit, but it would also measure zero voltage drop, more or less. So that's how you do that. All right, parallel circuits. Do some examples and be aware. You can make these things up as much as you want because they are self-checking. So go ahead and do a few. Just have fun with doing them. Get yourself ready for the next one, which is hybrid circuits. That's where it gets much more interesting. Thanks for watching.